Okay guys, this is our first video in our module on, I guess, modeling using exponential growth and decay functions or with logarithmic functions. So we're looking at things that I suppose that if you looked at a relationship between two variables, if you had a function that had some sort of relationship like this, or maybe we have some sort of decay relationship here. These models are going to be really effective at kind of representing that relationship, and we could even have, I suppose, a model that would represent something logarithmic that grows really fast at first, but then kind of just continues to grow really slowly out on the right. So that's what these models you see on the left here are really effective at doing, is representing specific types of exponential growth and decay functions and logarithms. So we're going to take a look at what these are really quickly here, starting with the first two. It says exponential growth and decay modeling. The thing I want you to notice is that they're both written as y equals ae to the bx. But what I want to make sure we point out here is this base e. What these really are continuous growth models. And so certainly we've seen continuous growth and decay models. And these were things that look like this, a equals pe to the rt. So I think it's worth pointing out that these two models are really our continuous growth model. And in terms of what are the values of importance here, the only really two values of importance that we tend to look at are our initial amount. Okay, so our initial amount, or our amount at time 0, and our rate, okay, that we tend to write as a decimal there. So the difference between them is that this negative right here, a negative rate is going to cause this to be decay if you see a negative there on our rate. So with respect to our remaining three models here, our Gaussian model is not one we're going to focus on in this section, but certainly it is a model that we tend to use when it comes to modeling averages. But logistic growth curves and logarithmic models, we're going to be using both of these down here. And you'll notice that the logistic growth model, looking at this, our x happens up in an exponent. It's in the exponent of this base of e. So this is considered to be an exponential model, whereas these bottom two models are just simple logarithmic functions that we may use to represent a relationship between two variables. So let's go ahead and take a look at our first one here, which is going to involve these continuous growth models, which will be really the meat and potatoes of what we do mostly. So it says the population P of a city is given by P equals 95,300 e to the 0.055 t, where t equals 0 represents 1996. So it says according to this model, when did the population reach 150,000 people? So we want to approach this both algebraically as well as graphically. I suppose what I would like to do, first of all, is just kind of represent what is going on here. And so in terms of what are the two variables in this problem, I suppose that I recognize that our two variables are p and t, where t is representative of time, and this is in years, and the p is the population, okay? And I guess this is in people. Sometimes we put like 95.3 and we say it's 95.3 in thousands, so 95.3 thousand. But this time we'll go ahead and use this true value here. And so when we approach this graphically, let's get our calculators on as well. Suppose we could go to y equals, when we type in 95,300, and this is e to the power of 0.055, and we have to use an x in this model here, and we're going to put an end parenthesis on this. But if I graph this right now, of course we're not going to see anything. What we need to do is just change our window. So with respect to what should I put for my window values here, well, if we're saying that our t is our time here, and our first year 0 is 1996, then that's like saying right here t equals 0, this is representative of 1996. And so how many years past would I want to go? Well, I don't know. I mean, we're looking at how long I have to wait till it gets to 150,000. That's quite an increase. And so maybe we go out like, I don't know, 20 years. So for my x-min, I'm going to type in 0 out to an x-max of 20. Let's go 25. And we'll go by 5 years at a time on this axis here. So we'll start at year 0. We'll go out to, say, the 25th year to begin with here. I don't want to put that on there just in case we end up changing that. But in terms of my y values here, well, what was our initial population at time 0? We're already starting at 95,300, and we're asking how long I have to wait to get to 150,000. So maybe if y is representative of our population, we'll go from 0 people up to like 200,000 people. Go past 150,000. And if I'm going to 200,000, if I was going to 200, I'd go by like 20. Maybe I'll go by like 20,000s here. So 20 with 3 zeros after it. If I hit graph now, I should see some representation of this. And so over the course of 25 years, we notice that it even outgrows 200,000 at the top there. So let's go ahead and get at least a representation of this here. In terms of our representation, we just want to make it seem like this. And I think it's important that we denote that at 0 years we have 95,000. We don't want to put a comma there. 300 people there. So in terms of what I'm going to anticipate that we want to do with almost all of these model problems is we're going to want to make a table that represents our variables also. And so I'm going to go ahead and put that data point on here. But this is going to help us kind of answer the questions we need to answer. So here's the situation going on here. What we want to do is ask ourselves this question, when does the population reach 150,000? So in terms of these problems that involve models, what you're going to see a lot of the time is I'm going to ask you for one of the variables. So when I say when, specifically we're looking for t equals what. So we're looking for t here, but I'm also going to give you a population if that's the case. So I'm going to put 150,000 on my table, and then my graph here, we're going to represent 150,000 is about right there. But we're going to trace it over, and we're going to trace it down, because truly this is what we're looking for right here, is what is this time at which our graph is at 150,000 people. So we know it's beyond 1996. What we want to do is plug this into our model now and solve for the time. So here's where our equation solving techniques are going to come in really handy. If our model is p equals 95,300 e to the 0.00055 t, then we're going to plug this in for population on the left-hand side of the equation. We get 150,000 is equal to 95,300 e to the 0.055 t. So now we're just going to solve this like we would any exponential equation. I suppose the first thing I check for is, could I write this one-to-one, but I wouldn't be very good at writing both the left and right-hand side as having a base of e, since that's some transcendental number. So let's isolate the base here of our exponent. We're going to divide both sides by 95,300. It would look like this here, 95,300. So on the left, you're going to notice something. I'm going to leave this as a ratio, and as a matter of fact, let's do this. At least we could simplify it a little bit. We could knock off these two zeros here, and we'll go with that for now. We might be able to simplify it further, but at least this would be a ratio we could keep as an exact value, and it's a little bit easier to write. So now that we have the base by itself, let's go ahead and take a log of both sides. We're going to want to use a log base e. So we'll do a log base e of everything on the left equals a log base e of everything on the right, and we'll use our inverse property of exponential things to undo this e to the power of 0.055t. So remember that when we do this, this natural log or log base e and this exponential expression base e cancel out. So on the right hand side we're going to have 0.055t. On the left hand side we just have this value here that we're leaving as an exact value, the natural log of 1500 over 953. So the only thing that we have remaining to do here, the only remaining thing to do is to divide both sides by this coefficient here. And so we get truly t equals the natural log of 1500 over 953, that value divided by 0.055. So here's where our calculator is going to come in handy. This, however, is our exact value. So once we get our exact value, let's go ahead and solve for our approximate value, which, if I quit out of this now, I suppose we could look at as being the natural log 1500 divided by 953. Now I have to end parenthesis that and divide that all by 0.055, and we get an approximate year value of about 8.25-ish. So I'm going to say about 8.25. This is being measured in years, so when we work with models we want to make sure we label units. And up here on the table I'm going to say 8.25. Over here on my graph I'm also going to label this that about 8.25 years we have about 150,000 people. So you can see that, we're using kind of the same model that we've been using to represent exponential growth or decay. It's just that now we're kind of less looking at, hey, at a given time, what's the population? We're going to be looking more at things like, if I give you a population, what's the time? So make sure you make a table. We'll plug in for one variable and back solve for the other there. But that'll be the process we look at a lot of the time.